is 0, or perhaps not through luck, perhaps by a good choice on the part of Microchip when they designed this chip, but it won't always work out that way. So as a habit, we probably want to set these bits. So let's go ahead and do that. So add con 1 bits dot VCFG1 is assigned 0. So that's going to be set A to D converter negative reference to ground, and then we're going to type add con 1 bits dot VCFG 0 is assigned 0, and that's going to be set A to D converter positive reference to power. Okay, so continuing on in our data sheet, next thing we get to this nice table here that explains how to set bits PCFG3, 2, 1, and 0. So what's this table all about? Well, we can see the AN 0, 1, 2, and 3 that was familiar to us earlier, and then here's the settings for PCFG 3, 2, 1, and 0. So what this table is all about is that you're choosing which pins are digital and which are analog. So let's go back to our circuit diagram here. So we'd like AN0 to be an analog input because it's coming from our potentiometer, whereas switch 1, 2, and 3 we'd like to be digital inputs. So if we look at the table here, this line matches that. AN0 is analog, and then AN1, 2, and 3, and in fact everything else all the way across are digital. So what we're going to want to do is we're going to want to set PCFG 3, 2, 1, and 0 to 1, 1, 1, and 0 respectively. And that will leave only AN0 as an analog input. So let's go ahead and do that. And once again, we'll copy and paste to make our lives easier. So add con 1 bits dot PCFG 3, 2, 1, and 0. So that's going to be set RA0, which is also pin AN0, to analog input. All other pins digital input. That last one should be a 0. So the value that we were trying to set is 1110, going from PCFG3 down to 0. So PCFG3 down to 0, 1110. Yep, that's correct. So now that we're done configuring our pins for either input or output in either analog or digital, let's take a quick overview of the configuration that we've selected. So on the first off, I apologize for my typo. The section in the center there in red, of course, pins for LEDs 0 through 3 and LEDs 4 through 7, that should say output, not input. Sorry about that. But in any case, referring to the 16 blue arrows on the left side, those are the 16 statements that are going to determine if our pins are input or output and analog or digital. So one thing we want to bear in mind here is that the tri-state registers, in our cases we're using tris A, B, and D, those take priority over pretty much every other register in the microcontroller as far as if a pin is input or output. So in other words, with the add con 1 statements, the bottom 4 blue arrows, we've set some pins, you could think of it as potentially to analog input and potentially to digital input based on what the tri-state registers are set to. But since we've set RB 3, 2, 1, and 0 and RD 7, 6, 5, and 4 to output, the statements at the bottom for the add con registers won't affect those because the tris bits registers setting those to output takes priority over the ADCON bits choosing what kind of input they would be. So in other words, on the right side of the diagram here, we've summarized our I/O pin configurations. So for RA0, starting with the left side of the chip at the top and working our way down, referring to the circuit diagram, we've set RA0, which is a shared pin with AN0 to analog input, and we've set RA1, 2, and 3, which happen to be shared with AN1, 2, and 3 to digital input. And then on the right side of the chip, because of how we've set our tris registers, regardless of what the ADCON register is set to, starting on the right side of the chip and working our way down, we've set RB3, 2, 1, and 0, which just happen to be shared pins with AN 9, 8, 10, and 12. But that doesn't matter because of the tris register state. We've set those to digital output. And then we've also set RD7, 6, 5, and 4 to digital output. Okay, so continuing on with our datasheet now, we've finished with register ADCON 1. So now we're going to configure register ADCON 2. And then we'll be ready to get into actually doing the analog to digital conversion. So bit 6 here is unimplemented. Bit 7 here requires a little bit of explanation. This is ADFM A to D result format select bit. So I made this separate picture to try to explain it. And there we are. So this register here, ADCON2bits.ADFM, this setting will allow us to choose where our analog to digital result will end up. And where the microcontroller circuitry is going to put that result is going to be in one of two registers. Now the issue we have here is referring to the datasheet. The 18F4550 is, as we see here, a 10-bit resolution analog to digital converter module, but the 18F4550 is an 8-bit microcontroller. So in other words, we have 10 bits, but only 8-bit registers to put those results in. So in other words, we're going to have to put that 10-bit A to D result in two different registers. So what we're going to do here, what the microcontroller does for us actually, is we have these two registers, ADR ESH, that's analog to digital result high, and then we have ADR ESL, that's analog to digital result low. So we can left justify our result, in which case the 10-bit result will appear here and then in the upper 2 bits of ADR ESL, or we can right justify the result, in which case ADR ESL will be full, and then in the lower 2 bits of ADR ESH will be the most significant of the 10 bits of result. So essentially we have a choice. We can choose between an easy way to do it, which will give us 8-bit accuracy, or a hard way to do it, which will give us 10-bit A to D conversion accuracy. So let's consider the hard way first. So if we choose to right justify, and then we take the value in these 2 bits of ADR ESH and we multiply them by 256, and then we add that result to ADR ESL and store the whole thing in a 16-bit integer variable, then we'll essentially have an analog to digital result that could go 10 bits, anywhere from 0 to 1023. But that involves a little bit more computation, and we don't really need that much accuracy since we have 8 LEDs, and we would like those 8 LEDs to show the binary values of 0 through 255 anyway. The 2 additional bits isn't necessary. So what we're going to do is we're going to do it the easy way. We're going to left justify it, and then when we have this situation, what we can do is we can simply disregard the 2 least significant bits of the result that'll be in ADR ESL and only use the 8 that are in ADR ESH, thus essentially giving us effectively an 8-bit conversion result, even though the microcontroller circuitry is really working with 10 bits. Back to our datasheet here. For this ADFM bit, we're going to want to left justify, so we're going to type ADCON2bits.ADFM is assigned 0. So that's going to left justify our A to D result, which effectively gives us an 8-bit A to D result in register ADRESH. That's A to D result high. Now the last two sections we have to set here are these bits TACQT, A to D acquisition time, 2, 0, or 2, 1, and 0, and then ADCS 2, 1, and 0, A to D conversion clock selection bits. The settings for these bits are a little bit on the complicated side. The ensuing pages of the document here gets into them in a lot of detail. A to D acquisition time requirements. It has this graph here. Then it gets into this analog input model where it justifies some calculations. Then they discuss temperature effects, and they introduce these formulas here to calculate all that. And then they have more verbiage here on selecting and configuring acquisition time and some recommendations and so on, and then a table on it, and it goes on and on. But to make a long story short, without getting into too much detail, basically these pertain to the timing of the analog to digital converter. So you can make the timing more aggressive to try and get a faster result, or you can make the timing more conservative, which will give you a slower result but a more stable result. Now, since we're using a clock setting of 8 megahertz, which is more or less in the middle of the range of what the 18F4550 is capable of, and let's take a quick look at the oscillator configurations so we can kind of justify that. So here's our table that explains the oscillator, or a figure rather. So if you're using the internal oscillator, you can go down to speeds in the low kilohertz range, 125 kilohertz, 31 kilohertz, etc. Whereas if you're using an external oscillator, you can end up with a clock that's as fast as 48 megahertz. We're using an 8 megahertz oscillator. We're using the fastest possible internal clock setting, which is roughly in the middle of the range of what the microcontroller is capable of, going from the fastest possible external clock to the slowest possible internal clock. So when we're looking at our A to D conversion, just as kind of a rule of thumb, for our A to D timing requirements here, if we pick values more or less in the middle, which matches our clock being in the middle, that'll give us a reasonably fast A to D conversion, but it'll still be stable at the same time. So we see the values here range from 20 down to 0. So let's choose the value 101, corresponding to 12. That'll be nice and in the middle of the range of the A to D acquisition time selection bits. And then, essentially we'll do the same thing for the A to D conversion clock selection bits. We'll choose 101, which will be FOSC divided by 16, which is roughly in the middle of the range from FOSC divided by 2 to FOSC divided by 64. So you can read these following pages of the data sheet if you'd like to get into that in more detail, if you ever have really demanding A to D time requirements. But for us for now, it's really not much of an issue. Just kind of picking nice mid-range values will work well for us. So let's enter that. Add con 2 bits dot ACQT 2 is assigned 1, and then add con 2 bits dot ACQT 1 is going to be assigned 0, and add con 2 bits dot ACQT 0 is going to be assigned 1. So that's going to set the A to D acquisition time for us. And then we're going to type add con 2 bits dot ADCS2 is assigned 1, and add con 2 bits dot ADCS1 is assigned 0, and add con 2 bits dot ADCS 0 is assigned 1. So let's comment that, set A to D conversion clock. Okay, so now what we're going to do is we're going to go back to